Okay, so let's go ahead and begin. Like I mentioned last class, today is mainly about lab 4. I'm gonna spend most of the time going over the lab 4 diagram class today. And then the activity is a little bit different today. It's not a paper activity, it's actually a demo. If you don't have a chance to show me today, you can show me next week as long as it's before the end of next Thursday's class. Remember, next Thursday we have the midterm. The midterm is the first hour of class. Okay, and then I have a short lecture afterwards, and then you'll have some time, to work on the lab, whatever labs you need to work on at that time. Do you have a question? How long is it? Say that again, please. It's a 60-minute. Well, you have 60 minutes to complete it, which I would think that someone's prepared and should be enough time. I don't know how many questions, but the topics. Remember, I put the topics on Canvas, and I had a handout that I gave everybody. If you didn't get it, it's on Canvas. But yeah, the midterm covers from the first day of class all the way through this class. It won't have any material from Monday of next week or Tuesday of next week. The lecture on Tuesday of next week, we're going to begin sequential circuits, which are circuits that have memory. So you don't have to worry about anything that we talk about on Monday. But yeah, everything from the start of the class through this class. So again, I don't think I'm telling you anything you don't already know, but I would definitely go through the activities that we've done, and I would go through the examples I've done in class. Now, if you didn't take notes, I think most people take notes, but if you don't take notes, I do have the recordings on Canvas, so you can rewatch the recording to see, what we covered in class. But as you're preparing and going through the different activities and examples, I would just make sure that you actually understand what's going on, because likely on the midterm there's going to be something that's similar but different, right? It's not going to be exactly what you did, but if you understood what you did, then you should be able to I would think anyway, of course there's no guarantees, but I would think you would be able to do what's on the midterm. But anyway, getting back to this. And if you have more questions about the midterm after I'm done today, if you want to ask, go ahead. But also with the midterm, real quick, you do have to take the test in your enrolled section. You can't take it with my other sections. You got to take it in the section that you're enrolled. And again, it's the first 60 minutes. So if you come in late, you lose that time. You won't have the full 60 minutes if you're late. Okay, but again, like I said, the activity today is a little bit different than previous activities because it's not a paper activity. It's actually a demo that each person has to show me. And again, if you don't get to it today, which I don't think most people will, as long as you show me by the end of class next Thursday, you'll still get full credit. And I'll talk more about what the demo is coming up. Okay, but before I go over the lab 4 diagram, I just want to briefly review some of the things we talked about during Tuesday's class that has to do with 2's complement signed binary numbers. Remember, we talked about 3 different types of signed binary numbers, but 2's complement is the most important, and it's what's important for lab 4. Okay, I think I might have mentioned this last time. I think of all the labs, this is the one that tends to give some people trouble, but I think the reason why some people have trouble with it is they're still kind of learning about 2's complement, and it seems a little funny to them. And so anyway, maybe if you do a little review and we talk about what this circuit is doing, hopefully it will strengthen or enhance what you already know about 2's complement. So to start with, if I have a positive number, but if we have two's complement and it's a positive number, what is this most significant bit going to be? It's going to be 0 because you call the most significant bit the what bit? Right, that's the sign bit. Right, and it's been agreed upon that when you have a two's complement binary number, in that sign bit, that most significant bit is 0, that's a positive value. So let's say I have this 4-bit two's complement number. What is that in base 10? Yeah, +3. So the 3 fingers, thank you. Right, because like we talked about last time, if you have a positive two's complement number, you just figure out the magnitude just like you would an unsigned, except the signed bit doesn't have numerical values. Okay, so if it's a negative number, the signed bit is a what? A 1. And let's say we have 1, 0, 1, 1. We know it's going to be negative, but what's the value going to be? 5. Is it going to be 5? Because how do we get the value when it's negative? What do? You flip it and add 1. Oh, there it is. 0, 1, 0, 0, and then you add. I think someone said 5. Okay. So everybody okay up to this point? Okay, we covered this. You did a bunch of problems, right? So, okay. Now, also, when we do binary addition, well, signed binary addition, or if we do signed binary addition, signed binary subtraction by addition, you always have to check your answer to make sure it's valid. And remember, I had 3 validity rules up on the board last time. Can someone give me one of them? So I hand back there. You want to give me one? Right, exactly. Yep. So positive plus a negative, always valid. All right. Who wants to give me another one? What's another? Right. You're adding 2 positives. Valid if the result is positive. Oh, again, if you just think of a number line, it wouldn't make sense, right, to add 2 positives and negatives. And then the third one, of course, is just adding 2 negatives. Is valid if the result is negative. Now, those are our validity rules, but I also pointed out last time that another way you could check is to see if your answer is within the range of values that you can get from that number of bits. That's like another way you can check it. Okay, but these are the 3 validity rules. So let's just do a couple of examples here. First, let's do this addition example. So again, when you add signed binary numbers manually, you do it the same way as unsigned. The only difference is this is the signed column, right? So 1 plus 0, 1, 1 plus 0, 1, 1 plus 0, 1. Then we have 1 plus 1, 0, carry the 1. And the signed bit of the result is in the same bit column as the signed bit of what you're adding. So what would you say about the validity of this addition? It's invalid, right? Because we're adding 2 negatives and we get a positive result, right? Doesn't make sense. So invalid. Now, you can also, now, this is something that's not required, okay? Last class, there was a number of people in all my sections that would come up. And because I was converting these to base 10, they thought like you had to do that. Okay, you don't have to, but I don't know. I think it's a good idea when you're first learning this to convert to base 10 just to make sure, you know? So we could convert both these to base 10 and then also see if this answer is invalid. So 1, 1, 1, 1. What does that equal to in base 10? And -1, very good. Right, because again, 1 for the signed bit tells me it's negative. So to get the value, I flip the bit to add 1. All right, how about this? Boy, you guys are really quick. You're a lot faster than my morning group. My morning group, I have to practically pry the answers out of it. I feel like a dentist sometimes with my morning group. So no, I appreciate that you're very quick with your answers. Thank you. Yeah, so -8, right? Because again, this one tells us it's negative, flip the bits, add 1. So we get 8. So you can see here, we're adding -1 and -8, which has a result of -9. And can we represent -9 with only 4 bits? No, because what's the most negative number I can represent with 4 bits? -8, right? Exactly. So that's another way to see that it's invalid. Also notice we got a bit to the left of the sign bit in the result. What do we do with this bit?
Let's start with that.
And you don't care. It doesn't make any sense, right? Okay. All right. So here's a subtraction example, but like we talked about last time, we do subtraction by addition. And what was the reason for that again? Like, why don't you normally see logic circuits that will subtract directly? Why do we do subtraction by addition?
Only means addition hardware.
Right, exactly. If you do subtraction by addition, you can use the same hardware that you use for addition, right? You don't need like a whole other set of hardware. Yeah. Now, the key is, like we said before, or said last class, right, A minus B is the same as adding A to the negation of B. In the way that you negate a sign binary number is by taking the two's complement, right? The verb. So, you know, if we call this our A and this our B, well, we just copy down A as what we have, but now we're going to add it to the negation of B, and we negate it by taking the two's complement. So that means you flip the bits and you add 1. Right? So we flip the bits. We add 1, 0, 1, 1. We add 1, 0, 1, 0, 0, 1. Okay. So that would be the negation of this. So that's what we add to here. And we would get 1, 0, 0, add the 1, 0, square sign. I think I did that right. But we can check, right? Because this G value that I started with here, what is this in base 10? 0, 1, 0, 0 in base 10 would be what? 4, right? Because it's positive, so you just figure out the value like you would in unsigned. So this is +4, right? And then when I flip the bits and then add 1, I end up with this. And what's this in base 10? Negative, because the sign, you see, this is the sign bit again. And then what do I have to do here to get the value of a negative? Flip it and add 1. So I flip it, 0, 0, 1, 1, add 1, you get -4. Okay, so you see, by taking this and taking the two's complement, I've negated it, right? Because we started with +4 and we made it -4.
If you take the two complement, flip it, then add 1. Each time you do that, like if you just do that over and over, you're gonna remain the same value, though, right? As long as you do it twice.
Well, yeah, any like two's complement number that you take the two's complement of,
Yeah.
right? You again the verb, it's gonna negate it. So whether you start with like a positive or whether you start with a negative, it always negates it.
All right, because I was just thinking, like when you add the 1, like you flip it then add 1, is that because like on the positive side you're actually adding 1, but on the negative side you're just subtracting 1? Or like I'm wondering why it doesn't actually increase the value of the number when you keep flipping it.
That's a good question. I mean, I don't have an answer off the top of my head. I'd have to think about it.
And also, let's say if our two's complement was 1, 1, 1, 1, and then we have to add, or before we add the 1 to it. So if we had originally all zeros, and then we flip it to get 1s, and then you have to add the 1, that's going to be like 5 bits then. So what do you? I'll flip 0.
Well, remember the furthest to the left bit is your sign bit. So that doesn't have numerical value. And if you have 4-bit two's complement and then you somehow end up with 5 bits, you ignore that bit to the left of the sign bit.
It makes sense to zero,
Yeah.
filter zero.
Yeah, so it's the same as what we've been doing here, right? Yeah, if you end up with a bit to the left of the sign bit, you just don't consider it.
Yeah.
And we'll see when we get to the diagram, when we get to the lab 4 diagram, we'll see how it fits into our hardware. Okay, but your other question, I would just have to think about. I haven't really thought about that, so. Okay, any other questions? Okay, but we should also just check this here. Is this a valid result? Yeah, it's valid. Why is it valid? Which rule is this? Yeah, you're adding a positive and a negative, right? So it's always valid. And then remember again, we just talked about this. Any bit to the left of the sign bit in the result, you just ignore. So we were taking, this is a 5, right, at base 10. And this is a -4 in base 10. So we were adding 5 to -4, and we get a result of 1, so it makes sense. Question?
Can you explain, or take the opposite of -8?
The opposite of -8. So you want to start with -8?
-8 minus positive.
So this would be -8, and you want to negate it?
Yeah,
So
I
you-
want to get positive.
Okay, well, you would negate it. Right, so I mean, you would flip the bits to start with, and then you would add 1. And let's see, what was that? We'd end up with the same thing, wouldn't we? Okay, so that very good. That would be an exception. Maybe that's what you were getting at. That would be an exception, right? Because you can't represent +8 with 4 bits. You can, yeah, so you can't negate like -8 unless you had additional bits. So that's a good point. Yeah. Was that what you were getting at?
Yeah, kind of.
Oh, okay.
Like,
Okay, yeah, I mean, you guys really are smart. Yeah, because you pointed out the one exception here, right, is that this will work. What we've been talking about with negating a value will work as long as you have enough bits, right? I mean, yeah, you're right. For -8, it won't work because you don't have enough bits. Yeah, I've never really thought about that, so I appreciate your questions. Okay, any other questions?
Do we put this formula sheet on a trend, like the sign annotation or documents?
No, actually, I'll have to double check and I can tell you definitely next week. But yeah, I don't anticipate supplying any information now. You need a calculator. Okay, but yeah, as far as what's on that sheet, understanding how to get the value from the bits when it's in Two's complement, I expect you to know how to do that. Because again, if the sign bits is 0, the way you figure out the value is no different than what we're doing for unsigned. The only thing that's new, so to speak, is that if you got Two's complement and the sign bit is a 1, to get the value, you got to put the bits in that. Yeah, and by the time you get finished with this lab 4, and plus I would think with all the activity problems you did last time, I would think that's going to be so ingrained in your brain. I don't think anyone would forget to do that. At least I hope not. Okay, but this was basically the review. Okay, we haven't talked about lab 4 yet, but before I start talking about lab 4, and I need to turn the camera. Any questions up to this point before we start into lab 4? Everybody's good? Okay, so this is the lab 4 diagram, the same that's on Canvas. I had it up here for my 8 to 11 class, and I think everything's right. I don't think I made any typos or omissions. Now, there is one omission, this right here. And this is the same as what's on Canvas, is that there is no internal signal T2. Remember, internal signals, those are what we declare in order to make connections between the lower level modules. So there's a T1, a T3, T4, T5, the T6, T7. But there's no T2. I'll explain why there isn't in a little bit, but I just wanted to point that out because usually if I don't, people will be, hey, there's no T2. But the first thing I want to ask you is, remember, we have this high-level black box diagram. And again, what's the main purpose of the high-level black box diagram? What does it show us or tell us the main thing? The main inputs and outputs, right? Kind of gave it away, the main thing. And remember, the dash box of your lower level diagram, inside, that's your structural model. Right? Outside the dash box, those are where your main inputs and your main outputs are. So you see in lab 4, you have 3 main inputs. Okay, you have A and B like we did for lab 3. Right? Those are the 2 numbers that are going to either get added or subtracted. And you have this additional input sub. Okay, and this is just a 1-bit input. Okay. And you got 3 outputs. Okay, seg and an, which were the same outputs as lab 3. Okay, seg is 7 bits. And an is 4 bits. Right, so just like lab 3, an is the anode that controls whether the display lights at all, and seg controls which segments will light. And then you have an additional output neg. Okay, this is just a single bit output. So in lab 4, you're going to have 9 switches, right? Because you're going to need 4 switches for A, 4 switches for B, just like you did for lab 3. And then you're going to need an additional switch for sub. And then you're going to have an LC or a 7-seg display, and then you'll need an LED for neg. Okay? All right, so the next thing we're going to do is step through this diagram to show what's happening. And we're going to start right here with this sub input. If I make this sub input 0, okay, so like on your basis board, you'll have a switch that you assign to sub in your constraints file. And then, you know, if you put that switch down, it will make sub a 0. Well, that sub input is connected to the select of this mux, so it's going to make that select a 0. And it's also connected to the CN of this RCA. Now, I mentioned this last class, that for this design, you need to take your RCA, your previous ripple carry adder, and you have to modify it by making the RCA all full adders. So you're going to replace the half adder in your RCA with a full adder. And perhaps some of you have already done that. Maybe you did that on Tuesday. Well, then also don't forget that some people in my earlier section today forgot this. You know, once you make this modification, you now have to test this and make sure it still works. You know, if you make a change to any module, no matter how simple that change may be, you got to check it, or at least it's smart to check it just to make sure it's still working the way you want it to work. So after you make that modification, sim it again with the 10 test cases you did previously, and then also add an additional 10 test cases where Cn is equal to 1, right? Because you didn't have that Cn input before. Okay, so make sure that you actually simulate that RCA after you modify. I can't tell you how many times people haven't done that, and then they get their whole circuit together and it's not working, and it's because the RCA is not working. Okay, so you all know how a mux works now, or at least you should, right? So if there's a 0 on this select line, what is the output of this mux going to be? Because how do muxes work? You have to do this for lab 3. Yeah, so which input would be connected to this output if the select is 0? Right. What's connected to input 0, which B connects directly to input 0. So B is going to be on input 0. Now, input 1 of the mux has an inverter between B and where it's at. So what am I going to have here at the 1 input? Not B, right? It's going to flip. It's going to flip all the bits. of the B value. Okay, so I've got B here, I got not B here. Well, if the select line is 0, that's gonna let B go through to the output. And now I'm gonna have B along with A, along with 0 at the input of my RCA. So all those three are gonna get added. And at the output of this RCA, I'm gonna have the sum of A plus B. Okay, so does everybody follow that? That makes sense? All right, now, if sub is 1, well, that's gonna put a 1 on the select line. It's gonna put a 1 on the C input. So what's gonna be at the output of this mux if there's a 1 on the select input? Not B. So now we're gonna have not B at this B input. We're still gonna have A at the A input of the RCA. So now when the RCA adds these three inputs, it's adding A to B that's been flipped and 1 added. So if B's been flipped and 1's been added, essentially what has happened to B? Right, it's been negated. We've taken the 2's complement of that B value, and now at the output, we're going to get A minus B, right? Because it will be A plus B negated. Okay? Now, the reason why there's no longer a T2 is because getting A minus B, getting the negation of B wasn't always done like this in lab 4. Okay? Years ago, I don't know how, it's been quite a few years now. Years ago, instead of modifying the RCA, we kept the RCA with the half adder, so we had to have another RCA here to add the 1. Okay, essentially doing this in 2 steps instead of 1 step. But by modifying the RCA to have all full adders, so you have that C in, so you can add 1 at the same time you're adding A to the flip of B, you're doing essentially A minus B in 1 step instead of 2 steps. Right, so when we had an additional RCA here, there was a need for another internal signal. And that's why you don't see it anymore, because we made the design more streamlined, if you will. Actually, Dr. Benson gets credit for that. She's the person that came up with this. Okay. All right. So are we good up to this point? Everybody sees how if sub is 0, we get A plus B here. If sub is 1, we get A minus B. Everybody good? Okay. The next thing we're going to look at is the validity checker. This you have to create from scratch. Okay. Again, you only have to modify this, but this you'll have to create from scratch. Now, notice it has 3 inputs, and 1 input is going to the 3rd bit of A, right? So the 3rd bit of this number. The other input here is connecting to the 3rd bit of B, the other number. And then the 3rd input here is going to the 3rd input of this result of this first RCA. Why do you suppose we have the 3rd bit of these inputs and output going into a validity checker?
It's the sign. So
Right, these are the sign bits. Right, these are the sign bits. Right, to check these rules, these 3 rules, I need to know the sign of what I'm adding and also the sign of my result. And then you can see there's just this 1 output valid. Right, when it agrees with those rules, right, we're going to have a 1 for valid. If it's invalid, we're going to have a 0. Now, there's at least 2 ways to code the validity checker. Okay, one way is to do an if statement. Right, you use an if statement to do them up, so you could use an if statement to do validity checking. Another way you can do it is you can make a truth table where on the input side of the truth table, you got A, B, S, right? You got each one of those sign bits coming in. And then you got your output valid. Now, how many rows is this truth table going to have since we have 3 bit inputs? 8. Right, so 0, 0, 0, 0, 0, 1, all the way to 1, 1, 1, right? So for each of those 8 combinations, you're gonna have to figure out whether it's valid or invalid by looking at our validity rules. And then you can take that truth table, go into a K-map. And then from that K-map, you can get the reduced expression for valid. And then in Verilog, just like you've done in previous labs, you can assign valid, right, to whatever Boolean expression you got, right, whatever reduced expression. So there's at least 2 ways. You know, these are the most popular ways, I would say. I've seen, this isn't as popular, but I have seen students use a case statement where they essentially concatenated these bits together, like they concatenate, join those 3 bits together, and then use those 3 bits in a case statement as the sensitivity variable. Okay, so there's at least 3 ways. There's probably even more, but these are the 2 most common: an if statement or doing the same approach that you took in the first couple of labs. Okay, but that you have to figure out. That you got to figure out. Okay, and you know which one you choose here. Like people will ask me, well, what one's better? Neither's better. It's just personal preference, really. Okay, each one is as good. Just different ways to do the same thing. All right, so let's look at the output side of this validity checker. Let's say that we have an invalid result. So the valid output is 0. That output is 0, that valid output of 0 goes to this input of this AND gate. This is an AND gate. And by the way, you should be able, or you should know by this point, the symbols for the different gates. Like you should recognize that's an AND gate. You know, it should be clear to you that's not an OR gate. Right? Because the OR gates have the curve, right? The curving input. Okay, this valid 0 also goes to the select of this mux. So let's look at this mux, because this looks a lot like what you had for lab 3, doesn't it, for the mux? Right? Remember in lab 3, you had a mux where the one input was all 1s and the other input was 3 1s and a 0. And in lab 3, what was that mux doing? Right. Now, in lab 3, in lab 3, it was determining whether the furthest to the right 7-segment display would turn on, or all the displays would be off by being connected to the carry out of an RCA. Here, instead of the select being connected to a carry out, it's connected to this validity or valid output. It was the same idea that if we have an invalid result and we have a 0 on the select line, well, then the data on the 0 input of the mux is going to be connected to the output. So we would have all 1s here. And remember, it takes a 0 to light up a 7-segment display. So if our result's invalid, we're going to shut off the display. So we're not going to see, you know, any number on our 7-segment displays if it's invalid. Okay. If it's valid, well, that will put a 1 on the select. And now the data on input 1 goes to the output. So we'll have 1, 1, 1, 0. So the furthest to the right segment would light up in that case. Also, if it's valid, it's going to put a 1 on this input of this AND gate. Okay. Also, when I have a 0 here, when it's invalid and I have a 0 on the input of this AND gate, if I have 1, 0 at the input of an AND gate, do I have to know what this other input is to know what the output is? No, because if I have just 1, 0 to an AND gate, what's the output going to be? 0. A 0. Okay, and that 0 is connected to this neg output, so it would also turn off the LED if you have an invalid result. Okay. All right. So, any questions about what this mux is doing? We're going to talk more about this AND gate coming up, and also the rest of this. But any questions up to this point? Okay. So now let's talk about what's going on here. So let's say that our result, whether it's addition or subtraction, let's say our result is positive. So that means our sign bit would be 0, right? Which is our most significant bit, which is bit 3. Now, I'll write some other bits here, but for what we're about to discuss, it doesn't really matter what these bits are. The important thing is what this sign bit is. Okay, so if it's positive, right? This is positive. Well, that 0 of the sum of this RCA, which is the same as the sign bit of the sum of this RCA is the same as the third bit of this T3 internal signal. And you see here, that's the other input of this AND gate. We're taking the third bit of T3, which is the same as the third bit of the sum of this RCA, right? Which is the sign bit. So if we've got a positive, this input of the AND gate is going to be a 0. And like we said before, if we have 1 0 to the input of an AND gate, the output's going to be 0. So you see, if we have a positive result, this input being a 0 is going to make neg a 0. Because we only want neg to light up when we have a negative result. Okay, the LED, when it lights up, will tell us that it's a negative number instead of a positive. Okay. Also, when the output of this AND gate is at 0, it's connected to this select of that mux. And this 0 input of this mux connects to the output of this sum here. So we would have, you know, the 0, 1, 0, 1, whatever positive number is here would also be at this 0 input of this mux. So when we have a positive number, we want to shut off the negative output, and we select the 0 input of this mux, which will put this positive number right at the input of our decoder. And you design this decoder, like this decoder, you don't have to modify, you just use the decoder just like you have in lab 3. So you're just going to have to copy it over from lab 3. Well, it's going to display, in this case, a 5, right? Because you made this decoder where it's a case statement, you know, 0 through 15. And from 0 to 9, it's going to show base 10 numbers. Now, once it gets more than 10, it's going to stop showing hex, right? Because that's how you design this. Okay. All right. So I haven't talked about this. This is coming up next, but so far, is everyone following? Does everyone see that this is a positive number? It's going to shut off the neg output, and it's going to select this input to go to the decoder, which is just going to be whatever positive number we have. Okay, so I saved the best for last. I say this for last because usually if someone has difficulty understanding how this circuit works, usually it's this second RCA. Okay. This second RCA only matters, it's only relevant when the answer is negative. Okay, when the answer is positive, when the result of this first RCA is positive, this has no effect. Okay, it's not used. Okay. All right, so let's say we have a negative result. Right, so if it's a negative result, this sign bit's going to be a 1. That's going to put a 1 at this AND gate input. Now, if the result is invalid and this other input of the AND gate is 0, well, it's going to shut off. It's going to shut off this LED for neg, and also if it's invalid, it's going to blank out the displays, right? So if anything's invalid, it's not going to show up, right? Because we shut off the displays. But if it's negative and it's valid, what's going to be at the output of this AND gate? A 1, because you got 2 1s coming in. That's going to turn on the negative output, right? So it'll turn on our LED to tell us that the number is negative. And it's going to put a 1 on this select of this mux, where now whatever's at the 1 input of this mux is going to go to your decoder. And that 1 input of the mux goes to the output, the sum output of this RCA, the second RCA. So let's see what the RCA is doing. Let's see what this is doing here. Well, look, between the A input and where the sum output of this first RCA is this inverter. So it's gonna flip. It's gonna flip whatever negative result we have here, right? So let's say it's 1, 0, 1, 0. Here we would have 0, 1, 0, 1. Also, we connect the B input to all zeros. And we connect the C in to a 1. So what this second RCA is going to do, it's going to take the flipped version of this negative answer, add it to 0, which is just the negative answer, and then add 1. So essentially what the second RCA is doing, it's taking that output when it's negative, flipping it and adding 1. So what is it doing? It's taking the 2's complement. It's taking this and it's giving you the value now, right? Because just like when you have a negative number, you flip the ones and add 1 to get the value. That's what this hardware is doing, right? So at the output here, if this is what's going in, it's going to flip it. Or, well, it's already been flipped. I'm sorry. It's already been flipped. So it's 0, 1, 0, 1. It's just going to add 1 to it. So you see what's going to go to your decoder is a 6, right? And this is -6 in 2's complement. Now, can you see what the problem would have been if we didn't have this hardware? If we had connected this sum output directly to your input of your decoder, if you have 1, 0, 1, 0 going into your decoder, the way you designed it, what would your decoder output? Because in your case statement for your decoder, where you have 10, right? Because 1, 0, 1, 0 is 10 in binary, right? What do you have your decoder outputting if you got a 10 going in? A, right? Because you designed your decoder as interpreting those bits as hex, right? Which is not what we're doing here. You know, another solution to this problem would have been to modify your decoder, right? To change your decoder so it wasn't doing hex anymore. But instead, we kept the decoder the same and added this circuitry to interface it to the decoder. Okay, so the reason why I step you through this diagram, one is just more practice with 2's complements, and also just some practice with just following how signals go through a diagram. Because this is literally what you do with diagrams like this. You just say, oh, okay, for this case, what do I have at this input? It's going to give me this output, and you just work your way from the input side to the output side. But the other reason for going over this is to help you to troubleshoot, right? Because this morning, my 8 to 11, there was a number of people, they modified their RSA, they checked it out, worked. They did the validity checker, checked it out, worked. Put everything together, didn't work. And in a couple of cases, works fine if the result is positive. If they add any numbers over here, if the result is positive, they'll get the right display. But any result that was negative, there was something wrong, right? Well, if you understand how the circuit works, if it's working except it's not displaying the right negative number, you're looking here, right? That's probably where the problem is, somewhere in this part of the circuit, right? Because this part of the circuit matters when you have a negative result, right? Like we said before, this has nothing to do when you have a positive result. There was another student that, for the overall module, everything was off by 1. Like their results, no matter whether it was a negative or a positive, the result was off by 1. Well, where would you immediately think there might be a problem if everything's off by 1? Yeah, probably something here, right? Probably something maybe with the CN, maybe something didn't connect right, or something wasn't, I mean, the person found what the problem was, but they didn't get back to me. I don't know exactly what it was, but it was probably some connection in the structural model that wasn't done right. Okay, so anyway, having some idea of what's going on in the diagram can help you when you have problems, okay, as opposed to just kind of like randomly trying to change things or look at things. If you have some sense of how it works, it gives you a better idea where to look when something's not working the way you expected it to. Okay, so any questions up to this point? Okay, did this help? When you first came into the class, did you look at this and say, oh, what's going on? But now you have some idea at least what's going on? Okay, good. All right, so I kind of talked about this a little bit, but let me go into a little bit more detail. Today's activity, again, it's not a paper activity. It's actually something that you have to demo to me. The first thing you need to do for this activity is watch this video. Okay, it's on Canvas. In fact, I'll show you where in a moment here when I pull the screen down. It's a video that Dr. Benson made. And in that video, she shows you how you can put any signal, any internal signal onto the timing diagram of your simulation. Because when you run a simulation, it just defaults to the main outputs along with whatever inputs you have in your test bench. But she'll show you in the video how to look at this output on the timing diagram, how to look at this output, all these outputs you can look at. So for the activity, I want you to demo to me. You actually have to show me on your computer or one of our computers that you can put this signal here, this T4, which is the output, some output of this second RCA, that you can put that on the timing diagram and show me. Okay, and again, this isn't due until after the midterm next week. Because like I said, I don't think everyone's going to get all this completed today. Some of you may, but I don't think all of you. In fact, I know all of them. Okay, one other or a couple other questions here, and then you can get started. I think we already answered this, right? We said this was yours. I forgot to write it down. But remember, I asked you how many rows in the truth table, so that would be how many test cases each. Okay, now, once you have your RCA all built and simmed and it's working, and once you have your validity checker all built and it's working, now you do the structural model where you connect this all together. And this is where, in that structural model, this is where you model the inverter, the AND gate, and also how you connect the muxes up to the data, and also the RCAs. In fact, you did that in lab 3, right? Remember, in the structural model, you connected this input to this data, right? This input to that data. You do the same thing here. Now, additionally, you have some RCA inputs that go to data. So you'd have to do like dot B in parentheses, V, 4 tick mark B, 4 zeros. Same thing here with CN. Okay. Oh, also, I forgot to mention this earlier. Notice that the carryouts of these RCAs are not connected to anything. Why is that? Why don't we care about the carryout of those RCAs?
I'd like the bits before the sign bit. Or
Exactly, exactly, very good. Yeah, see, these 4 bits, those are your sum bits. This is the carryout of the RCA. And like we said, when we do addition or subtraction by addition, and we have a result where a bit is to the left side of it, we don't care. So you see, that's why the carryouts aren't connected, because we don't care. There's a bit there, but we're not using it. Okay, so again, here's an example. Sometimes you don't use all the outputs that you have available. Okay, now, when you run this in Vivado, when you run a simulation in Vivado, it's going to give you a warning where the warning will be, hey, this output's not connected. But you just ignore the warning because you meant it not to be connected. But Vivado lets you know it's not connected, and in case that you meant to connect it, you just forgot. All right, but you just ignore that warning because again, we're not using the carry out. Okay, also the inverter. Okay, so you have an inverter here, and you have an inverter here. The way you take care of the inverter, like let's say this one right here for RCA2, is in your top module, your structural module, when you're making the connections. Well, when you make that connection for input A of the second RCA, you'll just go dot A, and then in parentheses, look at what's on the other side of the inverter. It's this T3 connection, right? This T3 internal signal. Well, you want A to be the inverse of that. So you'll just put tilde T3. Okay, so that tilde is what makes the inverse. Okay, then you have this AND gate. And if you think back to earlier in the quarter, I think about a week or so ago, or maybe 2 weeks, I guess it was 2 weeks. We were talking about the structural model for the first time when you did your RCA and you had that activity that had like 3 examples. There was like pizza and fruit and sort, I think it was. Well, if you think back to that activity, you had some assigned statements because those structural models had, a couple of them anyway, had gates. Like one had an OR gate, I think, and one had like an exclusive OR. Well, the way you model gates like that in your structural model is just with an assigned statement. So you can just put, assign, and then whatever the output is, see our output is T6. And you would just say equal to what the inputs are, and it together. It needs the ampersand for the and symbol. Now, it's a good practice that when you have assigned statements in your structural model, to put those assigned statements between your logic declarations, right? Because you'll have your logic for your internal signals like T1 and T3 and so on. And then, here's where you're making the connections, like you did with the RCA. I would put the assigned statements in between. Okay, in between where you declare the internal signals and where you start to make the connection. Put your assigns there. Okay. Let's see. Okay, also the test cases for your overall circuit, once you have everything together, those test cases are on Canvas. So any questions before I pull down the screen so I can show you a couple of things on Canvas, one being the test cases?
In the validity chapter.
Yep.
A, B, and C coming from.
Yeah, good question. Yeah, this is like shorthand. Instead of drawing a line from here over to where A is, and we're just taking the third bit. Right, because A is 4 bits, but we're just taking the third bit because that's the sign bit. So yeah, this is really like connected way over here, but if you drew a line over here, things get cluttered. So this is just like a short way of doing it. Thank you. All right. Any other questions before I pull the screen down and put the projector on? All right. Yeah, so first, okay, this is the video. Okay, this is Dr. Benson's troubleshooting video. Again, it's on Canvas. So watch this so you know what to show me or how to do what you need to show me on, for the activity. And then here are the test cases. Oh wait, that's left too. Test cases, lab 4. Right. And I know, again, the resolution's not good on the screen, but again, on Canvas, you'll see it much better. But what's really important is that you do these test cases, don't make up your own. They have to be these. And on the left are the A inputs, and on the right are the B inputs. Okay, so make sure you get this right, because if any of these test cases aren't the ones that we're asking for, you won't get credit. It won't be considered working 100% because these test cases were not picked randomly. There's reasons for each of them. Okay, they give every possible combination of, A being negative, B, positive, B, or excuse me, A negative, B positive, and A positive, B negative, and so on. It gives all the different combinations. And also, the values were picked in such a way that each value is covered at least once. Okay? Now, as you can see, this is in base 10, and you, in your test bench, you can list these test cases as base 10, but I would recommend that you put these in two's complement with the ones and zeros in your test cases, because that's what you're going to have to do with the switches. Right? So if you have everything with zeros and ones in your test cases, you can just look at that when you're running through the test cases, when you're demoing that your design works on the basis board. Okay, and this is where that handout I gave you should be handy, right? Because you have all the different 4-bit values on that handout for two's complement. Okay, let's see, is there anything else? I think that was it, the troubleshooting video, these test cases. You have any questions before you get started? Because the rest of the class, you have time to work on this lab. Okay, and again, this isn't due until the Friday after the midterm.
So when typically if you were to type in number like, let's say 9 in the test cases, it would just convert it to binary. It's like the needed binary. So we put like, it's 101, right?
Well, that's true. In the timing diagram, you can choose what base it's going to show.
Yeah.
Oh, go ahead.
But if you were to have like a negative number, says a no to do like choose complement for the entire thing, like how would that work? What would choose default?
Well, not if you choose binary. If you choose binary, it's just going to show the ones and zeros, and you have to interpret it as two's complement. But I think also in the simulation with the timing diagram, you can choose like a decimal. So it would show up negative decimal if you did that. Yeah. So, any other questions before you get started? Let's see, in this group, there was a couple of changes in groups. I sent emails to the people that it affected. So if you didn't get an email, then I didn't hear from anyone in your group and you're in the same group. But if you did get an email from me, please, if you don't know the new person, let me know and I'll introduce you. Okay, but I'm done. So you can start working on what you need to work on. And if you have questions, let me know.